let's go ahead and start. So the to-dos for today or for this week are these. First of all, PA5 and quiz 17 to 20 will be doing this Saturday. Okay. And for many of you, it might be a little bit devastating. Exam number 1 scores are out. And if you go to the exam 1 channel, you'll be able to see the distribution. And some of the students are asking exactly where you see the score, the grades. Yeah, so that should be coming into your email box, okay, the email you left when you're taking the exam. And we now move to the first topic of today, which is to start from the quiz. Okay, so this was quiz 16 that we have completed last week. It was fairly easy, so I see that all of you guys did really well. Now we move to the next quiz, which is still about RDT. Okay, anyone in chat room? There might be some, but the mood is probably a little bit low because I also play Chopin's Funeral March. Okay, so next is quiz 17. Yeah, so Mao, Chunmao, and Bingrui, good morning. Well, good afternoon. Juan is also here. Good. Yeah, this is the midterm week. I suspect that many of you guys probably want to make up for the assignments or the exams coming up. Okay, so it's okay because we have video recordings. So you guys can always come back, right, after the intensive exams to recap, okay, what's being taught. So today we'll start from quiz 17. This is still RDT 2.1. So this is RDT 2.1, but considering cases with bit errors. Okay. So you see on the left is the sender, FSM. On the right is the receiver, FSM. Identical to quiz 16. All right. You are asked to show the finite state machine transitions triggered in sequence under scenario 4, S4. So this is asking you to continue from scenario 3, okay, and send one more packet, but there is a bit error in the returned NAC. Okay, so this scenario is a little bit tricky. There's a bit error in the NAC coming back to the sender. Okay, so sender here sends one more packet, but the NAC coming back, there is a bit error there. Okay. But similar to S3, there will be no more errors afterwards. Okay, so why don't we work on this and see RDT 2.1 makes sense for you. Okay. Oh, wow, huh. Team 13, you are always very fast. Okay, but let's see. Let's wait, give time to the other teams. So guys, feel free to work on it. You do have some time. Oopsie. Ads from YouTube. I know, Boris. Glad that you guys are alive. Hi, Livia. Let's see, Mao. Mao also came up with T3, T13, T6, 12, and 4. Yeah, I think Boris, you're right, because we have in the specification, right? S4 is to continue from S3, and S3 ends at wait for call 1 from above. Wait, oh wait, I see. So you guys started from wait for call 1 from above. I think there might be a typo for team 13, right? Because that way when you send the packet you trigger T3, isn't it? Oh, okay, the initial state of S3. Good. No problem. Got it, Boris. Okay, I see several teams are typing answers up. Very good. I thought that after a week, you guys forget about the RDTs, the Reliable Data Transfer Machine. Yeah, so at the end of scenario 3, we actually ended at the sender machine. Wait for call for 0. Yeah, wait for call 1 from above. So we ended at the state on the lower right of the sender. And so when we are sending one more packet in scenario 4, we start from that state. Wait for call 1 from above. All right, I guess a week is a little bit too long. So why don't we do it this way? That Polly walk you through the state machine, okay? And see you guys can follow. So this is quiz 17 with the finite state machine, sender on the left, receiver on the right. And the blue circle indicates the states where the sender landed, and also the state the receiver ended when we complete scenario 3. So scenario 4 will start from wait for call 1 from above, okay, over here. And for receiver, we start from wait for 1 from below, here. Oh, there you are. Okay, good. Yeah, you guys all came up with the same thing. Yeah, so it takes a little bit of time to recall, isn't it? Now let's see whether we could, whether Polly can recreate what you guys had here. So the scenario is to send one more packet. So sender here, send one more packet, then we must be what? Triggering this transition, isn't it? Okay, so this will be the first transition we're triggering. And the condition is that there is a call from above, so we need to send packet. So we take, therefore, according to this transition, okay, and move to the wait for ACK or NACK 1 state. In the meantime, we take these actions indicated in this, the transition as well. First is to generate a packet, right? Make packet, and this is going to be packet 1, packet with sequence number 1. Second step, UDD send. Oh, just send the packet out. And so sender over here sends a packet to the receiver. Receiver is currently at this state, wait for 1 from below, and it's receiving a packet. Now, being at this state, the receiver has 3 options, actually, 3 candidate transitions to take. One here, another here, and you know what? Another here. Because these 3 states, the origin state, are all wait for 1 from below. Now, to trigger which of these 3 states depends on which of the condition, okay, for the transition hold. Now, according to the scenario, there is a bit error in the return NAC. Okay, I don't know if you guys get the hint. It must be a transition that we trigger such that it sends a NAC back to the sender. So which of these transition actually sends a NAC back? Let's check. This transition, sends NAC, cool. So it must be this one. The second transition sends ACK. There's a third transition also send ACK. Okay, although these 2 are sending different ACKs. So this is actually a OACK that's generated here at T11. This is generating a new ACK because packet 1 is received correctly. Okay, and so it's generating ACK for 1. This is actually sending ACK for packet, I think, 0. But scenario says we should be generating NAC, and the return NAC contains a bit error. So we confirm this is the second transition we trigger. Okay, so the condition must be we receive a packet and the packet is corrupted. Otherwise, NAC will not be sent back. But triggering T13 also meant we stay in wait for 1 from below state. And sending the NAC back means there'll be a NAC packet coming back to the sender. Sender currently being in the wait for ACK or NAC 1 state, receiving the packet, will need to decide which transition to take. It can be what? T6 or T4, depending on what's in the packet received. So T4 is the one that's more straightforward. That means we receive a packet and it's not corrupted, and it does carry the ACK number we are expecting. But you know what? It's a NAC packet that's coming back, right? So it must be triggering this, a packet, and it's a NAC. And it's a NAC with corruption, so it's actually fitting this condition. As we check, the NAC is corrupted. We didn't know whether it's a NAC or not. Okay, so we actually fit this condition here. As a result, we see we need to be triggering T6. So this is the third transition. According to T6, we stay in the wait for ACK NAC 1 state. And we send SNDPKT. This is the packet that's generated slightly earlier. That is packet 1. Because at this state, sender doesn't know if this packet is received successfully or not. Although it's not successful, but the NAC was not, so the NAC is also corrupted. So anyway, we retransmit the packet. So this transition is called, we stay in the wait for ACK NAC state, and then packet 1 retransmitted. And because there's no more bit errors afterwards, waiting here for ACK from below, waiting here for packet 1 from below, 3 possible transitions we take, but this time there's no more bit errors. So corrupt, this must not be the transition we're taking. It's not corrupt, but you know what? This transition is looking for sequence number 0, but we are receiving a sequence number 1, so this must not be the transition that's triggered. And therefore, this is the transition we're triggering. According to T12, we'll move as receiver to the wait for 0 from below state. In the meantime, we take these actions. Extract data, pass it up to the application layer, and we generate the ACK for packet 1. and send back ACK1. That ACK1 arriving at the sender currently at wait for ACK1 state, sees that the ACK packet is not corrupted and it's indeed ACK for packet sequence 1. Therefore, we take the state. Okay? And according to the state, the sender here moved from wait for ACK1 to wait for call 0 from above. So sender at this point is ready and can send another packet. And also in the meantime, we take action, which is null. All right, so sender here, wait for call from above. Receiver here, wait for ACK from below. So after sending this one more packet, 2 state machines stabilize and waiting for further actions. Okay, so this is quiz 7, and I hope that what Polly had here matches what you had also in mind. And those who couldn't quite recall RDT 2.1, hope that it's a little bit more clear this time with a careful walkthrough like this. And you know what? RDT 2.1 is super important. Let's take one more quiz, okay, and see if you get it. So quiz 18 is asking this. Okay, again, you see the finite state machines of RDT 2.1. Okay, so what I'm asking now is, in what case, okay, in what scenario would transition T16 being triggered? Where is 16? It's in the receiver, right? And it's a transition associated with wait for 0 from below. So this is when receiver is expecting packet 0 coming in. And T16 is what? The transition that is receiving a packet, and it's not corrupted. But it carries sequence number 1. But this is the state we are expecting packet 0. But the ACK is for packet 1, odd. That's why we stay in the state and wait for the real ACK 0 to arrive. But in the meantime, okay, T16 here is sending a packet that is an ACK packet, isn't it? And what ACK packet is sending? Yeah, it's the ACK packet that's being generated earlier here in T12. And T12 is an ACK for packet sequence 1. So, odd, right? So receiver supposedly receiving data 0, but as a result, receiver is, upon receiving a packet, it's generating ACK for 1. It's okay, let's take a little bit more time to think about it. I know Mao and Boris, you guys are really fast. That's great, that's great. But you see, for finite state machines and a distributed system like this, it's more important that you spend time to think things through. So you see, when the receiver is in the wait for 0 from below state, that meant also if receiver is in the wait for 0 from below state and receiving a packet, okay, and that packet says I have sequence number 0 instead of, actually, that packet says I am sequence number 1. That means, hey, wait a minute, right? The receiver is expecting packet 0, right? Wait for 0 from below. But data 1 came. Why? So if this is receiver just starting, okay, wait for 0 from below and it's receiving packet 1, that's impossible, right? Because if the whole system is just starting. So that means if the system just is not quite starting and waiting for 0, but receiving ACK1, that means there must be a packet that has been, an ACK that has been sent before and triggering the sender to send new data. Okay, so T12 at some point was triggered, okay, and ACK1 was sent. But sender here, receiving ACK1, is still sending packet 1. Okay, I think that usually is a little bit more obvious for many of the teams. Let's see what team 13 and 4 have here. When the receiver sends ACK, which is transition 12 with sequence number 1. So ACK1 is being sent by receiver through transition 12. Okay. So that ACK packet goes back to the sender. Okay. But sender somehow sends packet 1 again. Well, if ACK1 is not corrupted, right? Wait. Yeah, if ACK1 is not corrupted, then sender should be sending the next data 0. So that means that ACK1 must be corrupted. Therefore, sender sends packet 1 again. And packet 1 is coming back to the receiver. But right at that point, receiver sees maybe that ACK1 is corrupted, so it's sending ACK1 again. So that's what T12 is doing, retransmitting the acknowledgement because that acknowledgement was corrupted. So I think Mao is saying the same, right? Sender sends ACK1 to receiver, so receiver stay in wait for. The sender will go through T4 so that the next packet sent will be definitely. So, but these packet 1 is a retransmission. Yeah. So T12 there is definitely triggered by a packet 1. And T12 is retransmitting also ACK1. But the scenario must be because ACK1, the original ACK1 was corrupted going to the sender the first time. Okay. Send ACK to the sender, but the ACK was corrupted. Okay, very good. Somewhere gets it. All right, so Q18 here is a little bit tricky. Think about it. Now you see. Oh, team 12 shows, okay, receiver is expecting packet 0, but it's getting packet 1. And the packet is not corrupted. So the receiver sends ACK, and that is the OACK in transition 16. So the sender can go on. Yeah. Good. So I think Bingray gets it. Shengwei gets it. I think Chumao gets it as well, because T12 is doing exactly that. Gets packet 1, but this is not quite what's expected. Retransmit the ACK for 1. And so that will push the sender to send the next one, hopefully, if the retransmission of ACK1 is not corrupted anymore. All right. So that was RDT 2.1, and that's summarized RTD 2.1's finite state machine. Now, this slide is called discussion, but what it does is really the summary of 2.1. So at the sender side, what's being special is this. Sender checks whether the ACK-NACK is corrupted. Okay. Now, in order to prevent having duplicate packets, the sender side now also assign a sequence number to the data packet sent. So it's either 0 or 1. And in order to track data packets carrying the sequence number, there are now twice the amount of states and twice the amount of transitions. So the states somehow need to remember what is the expected sequence number. Receiver side, the primary function is to avoid receiving duplicate packets. So it would check the sequence number, whether it's a repeating sequence number. In that case, the packet is a duplicate. If that is the case, the data will not be extracted, passed up to the application. It's just going to be discarded. But be careful. Receiver here seeing a duplicate, although not extracting data, not passing it up to the application, it will still what? Send an ACK out again. Why? Because the former ACK or NACK being sent back to the sender. Yeah, only the sender knows whether the packet is corrupted. And if it's corrupted, the sender doesn't even know whether it's an ACK or NACK. So sender there is trying to be fuzzy and do the best thing that he can do, which is to repeat sending the data that has been previously sent. So receiver here needs to be more considerate. In case it's a duplicate packet, send back the ACK again, just in case it's an ACK packet being sent back and it's corrupted at the sender. Now, at least the sender will be informed. Everything is okay and move on. So that was exactly explaining why T12 is triggered. Yeah, so in T16, that ACK1 was corrupted going back to the sender. Sender, seeing that it's corrupted, retransmit packet 1. Therefore, at the receiver side, it sees packet 1 again. So the ACK or NACK packet can be corrupted, and that was the scenarios considered in RDT 2.1. That is a little bit more advanced than RDT 2.0. And now we move on to the next small version, RDT 2.2. Now this version is relatively easy. All it has changed is just instead of sending ACK, NACK, 2 different packets, we use just a sequence number for the ACK, 0 and 1, to differentiate whether this is an ACK or NACK. One packet, one type of packet to indicate whether it's positive acknowledgement or negative acknowledgement, instead of using 2 types, ACK type, NACK type. So this will reduce the overhead of the protocol and implementation. Now, the video. RDT 2.2, it's essentially the same as 2.1, except here. It's going to be the NACK-free version of 2.1. By saying that, what I meant is, well, in 2.1, when the packet arrives at the receiver, we send positive acknowledgement, that is ACK. Well, in case that data packet is corrupted, we send a negative acknowledgement, that is NAK. Now, as a result, we do have like 2 packet formats, right? One says I am acknowledgement, the other says I'm negative acknowledgement. So RDT 2.2 here is essentially to say, let's not have 2 different packet formats, just have 1. acknowledgement packet, but adds a bit in the acknowledgement packet, and we change the bit, okay, the value in the bit, to indicate whether it's really a positive acknowledgement or a negative acknowledgement. All right. So same functionality as 2.1, but using only ACK packet. But the ACK packet will be carrying an extra bit that is also the sequence number. Okay, so that is the sequence number bit. Okay, and the value in the sequence number bit is going to tell the sender whether this is a positive acknowledgement or a negative acknowledgement. All right. So now we have, a NAC-free protocol. Receiver sends acknowledgement packet for the last packet received. Okay. Think a little bit about it. So the receiver starting from waiting for call from below 0. Right? So if packet 0 is received okay, receiver here sends acknowledgement for packet 0. Because packet 0 received okay. The last packet received okay is what? Sequence number equals 0. Now, go to wait for call from below, packet 1. So if packet 1 arrives at the receiver and it's corrupted, what does receiver do? Which packet is the last received being okay? Well, 1 is not okay. So, still sending ACK packet, but sequence number bit there is 0 again. All right. But at the sender side, what's going to happen is sender will receive the first ACK with sequence number 0, right? Indicating packet 0 is received okay. But sender there is going to receive another sequence number 0 ACK. Ooh. Hey, how come I get acknowledgement for sequence number 0 twice? Having duplicate acknowledgement at a particular sequence number that indicates the next data packet that sender just sent out was corrupted. A negative acknowledgement in a way. So receiving duplicate is essentially signaling, sender is sending a NAC, right? So sender there will have to what? Retransmit the packet that's last sent. Now let's try to develop RDT 2.2's finite state machines. So here what we will do is to borrow from 2.1 and start from the receiver side of the finite state machine. All right, so initial state is wait for 0 from below. So we're expecting data 0. And we get 1 if it's not corrupted and indeed carrying sequence number 0. Then we extract data, pass it up to the application layer, generate an ACK packet with the checksum, and then send it out. Now, if it's 2.2, we'll be generating an ACK packet, all right, but this ACK packet should be carrying a sequence number, isn't it? And according to 2.2, the sequence number should be the last data packet received okay. And what is the sequence number of the data packet received okay? Well, we just actually received 0. So, you're correct. The ACK packet we're generating here for RDT 2.2 should carry sequence number 0. And so once we finish all the actions, we'll be finishing the transition and move to the next state, wait for 1 from below. And if we get packet 1 coming in, passing these conditions, so indeed carrying sequence number 1 in this data packet, then similarly, we take the data out, generate ACK, and send it out. And here, the ACK sequence number will be what? Data 1, the sequence number that we just received. So as a result, we could actually conclude the receiver side of RDT 2.2 should look more like this. And I'm ignoring the upper right part of the receiver's finite machine. So receiving a packet, not corrupted, carrying sequence number 1. The ACK packet will be generating, of course, it needs to be an ACK packet format carrying checksum. It also carries what? the sequence number of the data we just received, okay, and which is 1 here. So for this other transition at the top, then it will be make packet 0 ACK checksum. Now, hey, the receiver side of RDT 2.1 actually have all these other transitions, right? So we only handle this part and extend it to 2.2. We will still have to extend these transitions so that it will work for 2.2. Now, these are actually exact mirror of each other, so let's just focus on one side. Okay. Now, let's pick this transition first and see if we could evolve it as well into 2.2. So this is receiving a data packet, but it's corrupted. So in 2.1, we send a negative acknowledgement. But for 2.2, we don't send negative acknowledgement packets anymore because we don't have that format. Instead, we send ACK. But we have to carry a specific sequence number to indicate whether this is really a positive acknowledgement or a negative acknowledgement. So, yeah, the rule of thumb generating the sequence number there is what? Who is the last data packet received, okay? Now, receiver is currently waiting for data 0 coming from below. So what that means is that the last packet received, okay, should be carrying sequence number 1. So ACK here should give the sequence number of the data packet last received, okay. So yep, it should be ACK1 here that we're sending back to the data center. Now, what about this other transition? Receiving a packet, not corrupted, but carrying sequence number 1. This is not the data 0 we're expecting. All right. How can this be happening? Yeah, so this is the very odd situation where the previous data, ACK, being sent back to the sender gets corrupted, if you recall. Yeah, ACK packet or negative acknowledgements can be corrupted now, right, in version 2. Now, if negative acknowledgement is corrupted, sender simply retransmit, no problem. But if positive acknowledgement gets corrupted, sender also retransmit. And that is this situation here. You already sent back an acknowledgement for data 1, and yet it's receiving data 1 again. Yep. So this is the situation. ACK packet gets corrupted, and so you're receiving a duplicate of data 1. So we do not extract data and pass it up to the application because that's going to repeat words, repeat letters, repeat sentences. Okay. So we only send back ACK. And this ACK should be what? Acting the last packet received, okay, therefore also carrying sequence number 1. Okay. Now, if you look at this guy and this guy, both transitions, the actions they'll be taking will be identical now, right? Both sending acknowledgement packets carrying sequence number 1. So then perhaps we could just combine the two transitions. Receive a packet from below, checking if it's corrupted, or carrying sequence number 1, send ACK packet 1. Right? And you know what? ACK packet sequence number 1 is already being generated here. Send PKT, if you do not replace this variable's value, it will remain the same. And so if we just simply call this, then yeah, we just combine the two transitions and make it very brief, like this. RDT, either corrupt or carrying sequence number 1, simply send back the send packet that has been generated here, which is an ACK with sequence number 1. Now let's try to develop the sender's finite state machine. Again, let's borrow 2.1's sender finite state machine and start from there. This is the initial state. We wait for call from above. And if there is 1, then we generate starting from packet 0. And then we enter that wait for ACK state. Now in case a NAC is in, we do have this is NAC check, isn't it? So if that is the case, we retransmit the data. Otherwise, everything is fine, and this is a positive egg, so we do nothing and move to the next stage and gets a call again from above. But the thing in 2.2 is this. Well, there's no such thing as negative acknowledgement packet. In fact, both negative acknowledgements are just egg and carrying different sequence numbers. So this will also be a is egg check, okay? But the difference is going to be the sequence number they are expecting being different. So what should be the sequence number we expect here to pass so that we move on to the next state? We are expecting 0, right? So the sequence number here should be carrying 0. So we should be checking is egg and particularly sequence number being 0. Therefore, we can move on. Send the next packet. If everything goes well, we should be getting another egg packet, then carrying sequence number what? 1, because we just sent out packet 1, right? Now, the neck here, check can no longer be valid and will be also doing the is egg check. But what should be the matching sequence number here to trigger this action? Well, we just sent packet 0. If packet 0 was corrupted, the receiver would be what? Sending the last data packet received OK. So that should be what? Sequence number 1. Similarly, for the check here, it should also be is egg, but sequence number what? 0. And that takes us to the sender side of the finite state machine. So we change this line as well as this line. So this line is what? Expecting 0, so check whether the sequence number equals 0. This is also now is egg, and this should be carrying sequence number 1. And that was RDT 2.2. Okay. It's just another way of writing 2.1 so that it's more concise. And for the rest of the time, we'll go with the next quiz today. It's a fun quiz, in fact. Okay, so quiz 19 is actually Polly is taking inspiration from the Lord of the Ring. Okay, so this is the Battle of the Helm's Deep. Okay, so Helm's Deep is the land of the horsemen. Okay, horse people, and the Saruman troop is pushing in. Okay, to Helm's Deep. King of Rohan, the horseman people's king, has no choice but to call for help. Okay, and call for help from Gondor. So if you look at the map on the right, Helm's Deep is about in the middle of it, so that's circled. And Gondor is at the bottom of the map. What's challenging is this. Okay, so there's a wide mountain separating Helm's Deep and Gondor. And there are plenty of these orcs, okay, on White Mountains. Now, pretend that you are Gandalf the Wise. How do you make sure that you get help from Gondor? Okay, you send a messenger. Okay, the trouble is that the orcs eat people, okay. Isn't it? The message can be lost entirely. Mm-hmm. So how do you make sure that the message gets through to Gondor? So guys, this time it's not just that on the message there's one bit or one word that's there's a typo. No, it's not. It's that the messenger could be eaten by orc. So what would you do? Okay, and by the way, this is a very open question, so feel free. Okay, to apply magical solution, because that's a magical world. And with that said, and by the way, we have only 5 minutes till the end of the class. Okay, so those who type up your solution early, you're free to go. Yeah, probably understand that this is the midterm week. You guys are probably all distracted. So quiz 19 is also to set the stage for RDT 3.0. Okay, and this is the first quiz that it shows before we actually talk about the mechanism. But you see that as you're working on addressing, answering quiz 19, you also see that we know already some solutions to handle in case the messenger is just gone. And you might find that your solution is actually very similar to what RDT 3.0 takes. Yeah, I see you guys are probably still busy with quiz 18. Yeah. Okay, let's see what team 13 has. Okay, so number 1, send 5 messengers. Okay. Oh, okay, so maybe one of the 5 messengers get through to Gangdor. Okay, good. And then ask Gangdor to send something back, right? Yeah. So this way, Gandalf can confirm. Okay, so that message gets to Gangdor. Solution 2, use money or food to buy all the orcs. Ah, I see. Bribe the orcs, so prevent orcs from eating you. Good, so that the orcs don't. Summon a captain in an airplane. Oh, okay, so you fly through the White Mountains, so you go through another channel instead of running through the White Mountains. I see. Interesting solution. Oh, okay, number 4, summon a poor NTUEE student and ask him/her to deal with this problem. Yeah, I sense a little bit of resentment here. Yeah, I know, guys. Totally understand. I know. Sometimes, during the midterm week, you are just not enthusiastic of anything. It's really hard because you guys are all exhausted and anxious. So Polly offers a little piece of advice. What I do usually is just forget about that the results are coming out or the exams are coming up. Just do the best I can and move on. And by the way, guys, no matter what the outcomes are, Polly is still here. Loves you as always. All right, good. I see the other teams finally picking up some spirit and trying to type up their answers. That's okay. Polly will be waiting here for just a few more minutes. Oh, I see. Yo Wei for team 4. Send messenger to Gandalf, and the messenger should ask the people in Gondor to send messengers to Helm's Deep. The messenger heading to Helm's Deep should carry the message people in Gondor has already known. I see. Yeah. So Team 4 is saying that, let's assume the messengers get through White Mountain. But make sure Gondor sends someone to send a message back. That way, the Roham in Helm's Deep will know that the request for help has already arrived. Okay, so you send data over there, and you ask the receiver to send an acknowledgement back. Now, in case the receiver does not send a message back, then we know that the original request for help is probably gone, right? Yeah, so I think the remaining part of Team 4 solution is probably wait for some time. And if there's no confirmation coming back, then we might need to send another messenger. So resend another messenger. Maybe that's the step 3. Step 1, right? In the message to Gangdor, ask Gangdor to confirm by sending a message back. Step 2, wait for the message to come. If it does come back, then done. If it doesn't, then resend the original request for help. You know what, Team 4? You are on the right track. That's exactly what RDT 3.0 is doing. Yeah, Boris, Team 13, you guys' solutions are all quite wild, but I like those. Sending 5 messages is actually cool. That's another way to address potential loss in communication. And what's nice about sending 5 messengers is this. In case 2 of them are eaten, there will be still 3. Message will get through, right? So the sender side does not need to wait for some time for the confirmation to come, because 3 of them went through and confirmation will come. So sending 5 messengers can ensure that the confirmation come back timely. So that 5 messenger solution is not bad at all. Use money and food to bribe org to make sure that the message is sent through. Well, okay. Maybe that can be interpreted as to try to make sure that the whole path between Helmstedt and Gangdor is somewhat more reliable. It's no longer a UDT, unreliable channel, isn't it? Okay, I see. So the idea of sending 5 messengers more from the idea of when someone is using UDP, or when we use UDP to send DNS messages, right? If there's the first request did not get through, the local DNS server can send another one real quick. Okay, let's see what. Yeah, if there's no messenger coming back, resend. Team 12, brutal way, burn down White Mountain. So the Gangdor, okay, sure. Okay, so this is a little bit similar to make sure that unreliable channel being more reliable. But you know what? This is pretty much what we are doing currently on the internet. Because usually these packet losses or message loss are because there's not enough bandwidth on internet. Not enough memory space on the routers. So we have buffer full and then we drop packets. Yeah, so definitely making sure that the path between the sender receiver being more reliable is one way. Good, so redundancy is one way. Trying to retransmit as we discover that the message might not get through, another way. And to make the underlying channel more reliable, definitely, yet another way. Okay. But ask poor EE students to try to address this issue, or send EE students through White Mountains. Not a good idea. Not a good idea. Okay. All right. So Qi-en, send dozens. All right. Dozens of birds. So more than 5. That should add some assurance to the message arriving. Post a message on NTU 交流版. Tag and make your Gangdor friend. Okay. Through the social network. Assuming, hey, it's a magical world. There could be, right? NTU 交流版, D-card, or Facebook connecting Gangdor and Helmstedt somehow. Okay, so this is definitely a magical way at the time. social network. But anyone remember in the novel or in the movie how this is done? All right, so this is 5 minutes over the ending time. So let's call it a day now. Tomorrow, starting 10:20, we'll introduce RDT 3.0. Okay, RDT 3.0 there is closer to what Team 4 is saying. Okay, let's wait some time in case the confirmation did not come back. Retransmit. All right, so bye guys. Go off to the next lecture, okay, or to mourn the grades. So whatever the outcome is, again, let me assure, it's okay. Let's just move on. Okay, bye guys. Okay, bye.